Morning. Today's my lecture topic is the thermodynamics of the rocket engine. The thrust equation as developed above shows how the thrust depends on UE and PE for a given atmospheric pressure PA. Because the exhaust velocity is itself partially dependent on the performance of the nozzle and hence on PE it is not an independent parameter. It must be expressed in terms of PE and other independent parameters. It must be expressed in terms of PE and other independent parameters such as the temperature and pressure in the combustion chamber. To do this require the thermodynamic argument which treats the rocket as a heat engine. A heat engine converts the chaotic motion of the molecules in a heated fluid into the ordered motion of a piston, or in the case of rocket, a high velocity gas stream. In this process, the fluid expands and cools. The thermodynamic treatment will involve the equations relating internal and kinetic energy in the gas, and the equation of continuity for the gas flow through the nozzle. For our purposes, it is sufficient to assume adiabatic expansion strictly, isentropic expansion with no change of energy between the rocket and the ambient. In a real rocket, heat loss to the wall is significant and this will later be qualitatively. The first part of the derivation concentrates on the conversion of thermal energy into kinetic energy. This occurs in all heat engines and there is an analogy between the steam of internal combustion engine and rocket engine. For the internal combustion engine, we say that the air-fuel mixture is being compressed, then after ignition, it expands at a constant pressure from 2 to 3 as the piston moved. The same way, in the rocket engine analysis, the internal combustion engine, there is no inlet stroke as the rocket operates in a continuous chamber. Instead, if we think a fixed quantity of propellant introduced into the combustion chamber over a small time interval, we can follow a similar sequence. The propellant, fuel and oxidizer enters the chamber at the combustion pressure, so 1 to 2 is not appropriate or may be thought as fast as the compression developed by the external turbo pump. After the propellant ignites, the gas expands at a constant pressure through the combustion chamber until it enters the nozzle. At the nozzle, it begins to expand adiabatically as it passes through the throat and continues to expand until it exhausts at 4. There is no separate exhaust stroke because the rocket is not reciprocating. The thrust equation can now be elaborated in thermodynamic terms by considering the conversion of heat into kinetic energy embodied in the exhaust velocity UE and the mass flow rate m. The exhaust velocity of the propellants is depending upon the propellants enter the combustion chamber, mix and are ignited. The gas produced is heated by the chemical energy of the combustion and expands through the nozzle. This is a continuous process, but it can be analyzed and sensible results derived by assuming that the heating and expansion are two successive processes. This can be done by imagining a small fixed mass of gas and following it through the rocket. The exhaust velocity can be derived by setting the kinetic energy of the exhaust gas equal to the change in enthalpy of the gas as it cools and expands through the nozzle. This is assumed to be under isentropic conditions, that no heat escapes from the gas to the nozzle walls and the exhaust is assumed to behave like a perfect gas. The change in internal energy for our assumed mass of gas given by the well-known expression Cpm into TEC minus TE, where Cp is the specific heat at constant pressure and Tc and Te are respectively the temperature of the gas in the combustion chamber and the temperature of the gas at the exit plane of the nozzle.